across the copper wire. The magnetic field causes the free electrons to move in the same direction. If we wrap the copper wire into a coil, we can fit more copper atoms into the magnetic field and we can therefore move more electrons. This gives us an alternating current. Instead of someone moving a magnet back and forth all day, engineers instead just rotate it and then place a coil of copper wire around the outside. We split the coil into two but keep them connected and then place one at the top and one at the bottom to cover the magnetic field. When the generator starts, the north and south pole of the magnet are directly between the coils, so the coil doesn't experience any effect and no electrons move. As we slowly rotate the magnet, the north side passes the top coil and this pushes the electrons forward, so we get positive values. The strength of the magnetic field increases as it rotates up to its maximum where the most electrons are flowing. The magnetic field then starts to decrease and less electrons flow until the magnet is again directly between the two coils. Then the south pole rotates in, but this time it pulls the electrons backwards, so we get negative values. This again increases in strength up to its maximum and then decreases back to zero where the magnet is between the two coils. If we plot these values, then we get a sine wave. The north side pushes the electrons forward, and as the strength of the magnetic field increases, more electrons flow up to a maximum point. Then we're leaving the north magnetic field, so the number of electrons decreases down to zero. Then the south pole pulls the electrons backwards, so we get the negative values up to a maximum and then back to zero. This one circuit gives us a single phase supply. If we added a second coil set 120 degrees rotation from the first, then we get a second phase. This coil experiences the change in magnetic field at different times compared to the first phase, so its waveform will be the same, but it will be delayed. The second phase waveform doesn't start until the magnet rotates to 120 degrees rotation. If we then add a third coil 240 degrees rotation from the first one, then we get a third phase. Again, this coil will experience the change in magnetic field at a different time to the other two, so its wave will be equal to the others except it will be further delayed and will start at 240 degrees rotation. When the magnet rotates multiple times, it eventually just forms an unbroken three-phase supply with these three waveforms. With this design, we need 6 cables, but we can join them together in either a delta or Y method. For this example, I'm going to use a Y or star method because I think it's easier to understand. With a star configuration, we need just 4 cables, one for each of the 3 phases and then a neutral. Sometimes you don't need a neutral, but we'll look at that in our next video. When the magnet completes one full rotation, the electrons will have moved all the way forwards and then all the way back to their original position. We call this a cycle. We measure cycles in the unit of Hertz or Hz. If you look on your electrical devices, you'll see either 50 Hz or 60 Hz. That's the manufacturer telling you what type of supply the equipment needs to be connected to. Some devices are able to be connected to either, like this charger. Each country uses either 50 Hz or 60 Hz. North America, some of South America, and a couple of other countries use 60 Hz. The rest of the world uses 50 Hz. 50 Hz means the magnet completes 50 rotations per second. 60 Hz means the magnet completes 60 rotations per second. If the magnet makes a full rotation 50 times per second, which is 50 Hz, then the coil in the generator experiences a change in polarity of the magnetic field 100 times per second. So the voltage changes between a positive value and a negative value 100 times a second. If it's 60 Hz, then the voltage will change 120 times per second. As voltage pushes the electrons to create electrical current, then the electrons change direction either 100 or 120 times per second. We can calculate how long it takes for a single rotation to complete using the formula T, time, equals 1 divided by F for frequency. A 50 Hz frequency supply therefore takes 0.02 seconds or 20 milliseconds to complete. A 60 Hz supply takes 0.0167 seconds or 16.7 milliseconds. Now we saw earlier that the voltages from your plug sockets are different all around the world. These voltages are known as the RMS value or the root mean squared value. We're going to calculate that a little later in this video. But the voltage coming out of the plug socket is not constantly 120 or 220 or 230 or even 240 volts. We've seen from the sine wave that it's constantly changing between positive and negative peaks. The peaks are actually much higher. For example, in the US, the voltage at the socket can reach 170 volts, Europe reaches 311 volts, India and Australia reaches 325 volts, and the UK reaches 339 volts. We can calculate this peak or maximum voltage using the formula V RMS multiplied by the square root of 2. I've already worked these out for you on screen now. Because the sine wave passes through the same points in both the positive and then the negative half of the cycle, we get the same instantaneous voltages along the cycle, but they are either positive or negative. If we added these all together, then we would get 0 volts. So we need another way to calculate this. Luckily for us, some intelligent person came up with the idea of using the RMS value. Basically, they worked out how much heat an electrical heater could produce when connected to an AC alternating current circuit, and then they connected it to a DC direct current circuit and increased the voltage until it produced the same amount of heat. They then worked out a formula we can use, that being the square root of the squared average instantaneous voltage. I've just calculated what that would be for the wave on screen now, and you can see that the sine wave with 170 volt peaks comes out to 120 volt RMS, which is what we get at the plug socket. So now we've seen how to calculate the basic VRMS. Now let's slowly rotate the generator and calculate the voltages which cause the sine wave for each of the 3 phases. Let's first divide the rotation up into segments 30 degrees apart, giving us 12 segments. We'll cover the instantaneous voltage at each of these rotation points for each of the 3 phases. Now I'm using Excel to calculate these, and if you want a copy of my Excel sheet with all the calculations in, then I'll leave some download links in the video description below. For the video worked example, I'm going to use 120 volts VRMS. The sheet will update itself, plot the phase waveforms and give you the calculations. Again, links down below for that. So we first write out a table showing each of the segments and then the angle of rotation in degrees. First we need to convert each segment from degrees into radians. We do that by using the formula radians equals degrees multiplied by pi divided by 180. So we calculate the radian value for each segment and fill in the chart. Now we want to calculate the instantaneous voltage at each of these 30 degree segments. We calculate the instantaneous voltage at each segment using the formula Vmax multiplied by sin angle in radians. As I said, for this example, we'll be using 120 volts RMS, and as we calculated earlier, that gives us a Vmax of 170 volts. So just complete that calculation for each segment until the table is complete for one full cycle. Now if we plot this, then we get a sine wave showing the voltage at each point during the rotation. You can see now how the voltages increases with the rotation of the magnet, and when the polarity of the magnet changes, the voltages become negative. Now we can calculate phase 2 voltages, and we can do that using the formula Vmax multiplied by sin angle in radians minus 120 times pi divided by 180. This end part, 120 times pi divided by 180, just takes into account the delay because the coil is 120 degrees from the first one, and then it converts this to radians. So just complete that calculation for each segment until the table is complete for one full cycle. We can now plot this to see the waveform for phase 1 and 2, and how these voltages are changing. For phase 3, we need to use the formula Vmax multiplied by sin angle in radians minus 240 times pi divided by 180. So just complete that calculation for each segment until the table is complete for one full cycle. We can now plot this to see the waveform for phases 1, 2 and 3 and how the voltages are changing. So this is our 3-phase supply showing the voltage for each phase every 30 degrees rotation of the generator. If we try to add these voltages together, we get 0 because they cancel each other out. So instead, we're going to take the RMS voltage per phase. I'll just show you this for one phase, but the process is the same for phase 2 and 3. So we start by first squaring each instantaneous voltage for a full rotation. Now take the average of these values. Add them all together and divide by how many segments you have. In this case, we have 12 segments. Do not include the value at 360 degrees because this is a full rotation, so 360 degrees is back to start, which is 0. If you include this, you'll be counting the 0 value twice and your calculation will be higher. Now we take the square root of that number. This gives us our RMS voltage of 120 volts. This is the phase voltage. That means if we connect a device between any phase and the neutral line, then we get the VRMS of 120 volts. We can do the same for phases 2 and 3 and we'll get the same value. To get more power, we can connect to all 3 phases. We calculate the supplied voltage by squaring each of the instantaneous voltages on all 3 phases. We then find the average for each phase individually. And then we add these 3 averages together. Then we take the square root of that number. you'll see the three-phase voltages comes out to 208 volts. We call the smaller voltage our phase voltage, and we get that by connecting between any phase and the neutral line. We call the larger voltage our line-to-line voltage, and we get that by connecting between any two phases. That's how we get more power from the supply. Okay, that's it for this video, but if you want to continue your learning, then check out one of these videos